do it. Yeah, so last week we ended up with categories, which were this fancy version of monoids, right? So if you had a monoid, it meant you had an object type, and then you can sort of combine two values, and you also had a placeholder value that was sort of a unit for the combination of two values, which meant that it was basically getting absorbed by the multiplication and letting the other value shine. And then we saw that we could sprinkle some extra types on top of this, so that now we had the type of objects, and we had the type of morphism, which was indexed by these objects. So there's a source and a target, the idea being that we're moving along a path, right? And so just like for monoid, you have a way to combine two morphisms. Now there's just this extra constraint that they need to agree on where the first ends and the second one starts. And then the source of the first one becomes the source of the composition of them both. And the target of the whole composition is the target of the second one. So it's really formalizing that idea of composing paths along a set of values. And then we saw that the thing that corresponds to the unit in the monoid is now this identity morphism, which goes from any object whatsoever just to itself and doesn't do anything. And how do we formalize this idea of doesn't do anything? Well, it's the same laws as the unit laws for the monoid, for monoids, except that here we have this type index thing. So if you look carefully, you should see, well, everything is implicit, but if you look extra hard, you might see the implicit values showing up. Here, this is taking you from S to T, and here on the right-hand side, you have the identity at T, because otherwise the composition is not well-typed. And this is equivalent to X from S to T. And you can also do it on the left, but then it's a different identity. It's the identity at S. The whole point is that it doesn't matter. All of these identities behave in a way that is completely neutral with respect to the then composition operator. And then the other thing that we had in monoids is that combining two values is associative. So, or as we said the other day, the brackets do not matter. And so here you have the same law. You need a bit more setup because you have all of these indices in between that are showing up. But as long as everything is properly type aligned, so M1, M1, M2, M2, this is T, whatever, then you can group the composition in whichever order you want, just checking the difference, yes. And you will get the same result. Okay, so we had suggested one possible category last week, which was the category of, maybe I'll start with this one. So let me import some stuff. So we were saying that the objects were natural numbers, and the morphisms, which is maybe a bit strange, but they were proofs that a natural number is less than another. And then if you think about these proofs, it's quite clear that if you know that something is smaller than something which is smaller than something else, you could jump directly to the bigger element without making the argument via the middle one. So that should hopefully work well. Not properties. Well, maybe I'll just import all of it because I'm not sure what I want yet. So cat. So just like for monoids, we can define them by co-pattern matching. So we're building a big record by k-splitting on the goal. When there's nothing on the left-hand side, it will just produce all of these projections. And then I have to fill in the values one by one. So the object here, so just to remind you, they're sets, and we say there was the natural numbers. Oops, it's the wrong n. And the morphisms, so they're something that's indexed by two natural numbers, and here we're going to use the less than relation. Okay. And then is what you'd expect, right? If the source is less than the middle element, and the middle element is less than the target, then the source is less than the target. And that's transitivity. Oh yeah. Oh, I think it's just called less than trans. Yeah, there we go. Then there's identity. So if you remember, the identity proof is just that any object is related to itself, or you can move from any object to itself via the boring morphism. And so this will just be the proof that less than is reflexive, because for any s, s is less than s. And then associativity, well, okay, that's a bit more noisy, but you need to prove that no matter which three proofs you get as arguments, if you compose them left to right or right to left, it doesn't matter. But in this instance, because proofs are boring, we're actually golden, because there is a proof in the standard library that all proofs that m is less than n are equal to each other. It doesn't even matter that they were built this way. You could say, you could pick any other proof s to t, and you would have the equality always, because the only thing that matters is the start and the endpoint. In between, you're just counting the number of successors between s and t, basically. So I'll take all three of these, and I think I have something like, if I can type it, less than irrelevant, I think. Yes, and then I'm hoping it will manage to infer the left and the right hand side. And so if we jump to the definition, less than irrelevant is saying that this relation is irrelevant. What does it mean to be irrelevant? It's exactly what we want. Okay, it's using a different notion of equality, and okay. So it's saying for any values, any proof is irrelevant, and finally, hopefully, this is what we meant. So if you get two proofs that m is less than n, they are equal to each other. So there's a lot of unpacking, because there's a lot of structure in the standard library. And then we need to prove that if you apply transitivity to any proof and identity morphism on the right-hand side, you get your original proof back. But as we've just seen, these proofs are extremely boring, so we can just have this for free, and we can have the next one for free also. Okay? Fred, do you want to share with us your favorite category?
Well, which one do you want?
Your favorite? I don't know.
Okay.
I hope I'm near enough to the microphone to say, you've seen two degenerate kinds of categories. You've seen monoids, where there's nothing interesting in the objects. There's one object, and it's all about the connections from that object to itself. So think of the natural numbers as one object category where a number is a morphism, and you're counting the number of times you hop on the spot. Whereas what we've just seen here is a pre-order. It's a degenerate category in the sense that the objects are interesting, the numbers are different from each other, but there's nothing exciting in the morphisms other than their existence. So, we've got this irrelevance property. So they're two classically kind of differently degenerate variations on the theme of category. But with categories, the objects are interesting, the morphisms are interesting, and life's beautiful.
So, Guillaume, did I understand you correctly when you suggested that my favorite category might be the category of monoids? Right? Yep. Okay. I'm not sure if that's true, but I can introduce the category of monoids. So last week you saw, this is what you just said, right, Connor, that if you have a monoid, you can kind of upgrade it to a boring category. but, or boring or not, it's as interesting as the original monoid, right? But we can also consider a category which consists of all the monoids, so it's a different level, right? So rather than having a particular monoid, making it into a category, we can organize all the monoids into a category. So I guess we'll call this monoid cat. No?
I think there might be size issues, but let's see.
Yeah, but maybe that's a good thing.
Was it?
Okay, so to give a category, you have to say what are the objects, what are the morphisms, what's this composition, what's the identity, and prove that it satisfies the laws, right? So an object in this category, I want to be just a monoid, right? And let's see if Agda will allow this. And we see, unfortunately, that what I have, the type of monoids, is a set 1. So that's a large thing, because a monoid contains a set. And there are certain paradoxes where you don't want to have the set of all sets, for example, right? Because then that would lead to a contradiction, and then we could prove anything. So Agda is avoiding this by having a hierarchy of sets, and then large sets, and then very large sets, and then very, very large sets, and so on. Which means here that since we just defined a category to have an ordinary set, not a large set as the type of objects, then we are now formally in trouble, right? But there's also a way to turn off this checking, so I think that's what I'm going to do.
Okay.
Okay, so I've turned on the option type in type, which now says that set is a set, right? So it's just collapsing this whole hierarchy of large set, large sets, and so on into just the smallest part of it, which is very convenient because it avoids this problem, but it also means that we can now formally prove false using this if we wanted. So we just have to promise not to do that, right? And there are other ways to do it where you can have kind of universe polymorphic things where it's a set L for some level L and so on. But I think if we go that way, then that's just going to be distracting from the main idea. So it looks like we have the same problem, but now Agda will just accept that set 1 to be a set, right? Because all I want to do is I want to organize all my monoids into one category, right? And then formally then I should have a large category and so on, but let's not do that. Okay, so my objects are monoids, and then I have to say what is a suitable notion of morphism between monoids. So given a monoid M and a monoid N, what is the set of morphisms between them? And there could be many different options here, right? There is no really a right answer as such. It needs to be something, so I have a notion of composition, I have a notion of identity, and these need to be associative, and the identity really needs to be the identity for this composition. But there's no unique answer here, right? I mean, I could just use functions between the underlying sets. Functions has a notion of composition and identity.
You could say that M needs to be equal to N.
Yep. So I could insist that M is equal to N, and otherwise I'm not happy. I could have functions that preserve the unit, but doesn't preserve the monoid multiplication, and so on. So it really is a choice, and I'll get, for each one of these choices, I get a different category, right? But if I want the category of monoids, which if you went to look into a textbook and they would define the category of monoids, then they would probably take the morphisms to be the monoid homomorphisms, right? So the functions that preserve the monoid structures, it's preserving the unit and it's preserving the multiplication. Just because that's a nice category to work with. It will have some nice properties, right? Whereas if you choose something else, then might not have as many nice properties. So did we have a name for this?
Yes.
So it's just called homomorphism. Okay. Copy that. Okay. So homomorphism says that, well, if I give it two monoids, S and T, then it's going to give me the set of monoid homomorphism from S to T. So that's exactly what I want here. Right? Okay. And then here now, if I'm given a homomorphism from S to M and a homomorphism from M to T, composition is to produce a homomorphism from S to T. Right? So I need to be able to plug them together. And did you do this last week?
You can jump. I don't think we did.
No. Okay. Let's do it ourselves. Right. So I get.
Do check because the proofs are going to be annoying.
Yes.
Oh no, we just gave one.
Yeah. There's nothing mentioning composition in here. Okay. So I'm given a homomorphism F, I'm given a homomorphism G, and I have to make a homomorphism from S to T, right? And these homomorphisms, that's a record. So we make one of these by filling in all the fields. So I can do that by another co-pattern matching where I just pattern match on the result. So I have to say, okay, now this is kind of horrible. Let me just bring this back.
Oh, is it because it's in the face?
Oh, except
It's trying too hard to be clever.
okay. So now here I have to give a function from S to T, but I wonder if I want to open homomorphism in here maybe. Okay, let's just go with it. But F comes with a function from S to M, and G comes with a function from M to T, right? From the carrier of these things. So I should be able to just compose F and G. So if I do homomorphism dot function F, that takes me from S to M. And if I do it with G, that takes me from M to T, right? So all in all, do we have composition? Is that the wrong kind of? Okay, I guess I'll throw in the identity function as well. So if I do a function composition of two things, then here the first one should take me to T. So that's going to be my homomorphism dot function G. Is that right? Yeah. And then this is going to be the same thing for F. Okay, and then I have to show that this function I just created, that it respects mempty and it respects the multiplication, right? So if I apply F to mempty of S, and then I apply G to that, then I should get the mempty of T, right? Is that a problem? Well, the F and G are respecting mempty, right? So F applied to mempty of S is going to be mempty of the thing in the middle, and then G applied to mempty of the thing in the middle is going to be mempty of T, so that's hopefully fine, right? So here I have that mempty of the thing in the middle is the mempty of T. That's good. Did you use equation of reasoning last time?
You could, or you could use rewrite.
Yeah, okay, fair enough. So if I just rewrite by this for f first then, right, that should hopefully turn this f of mempty into a mempty. Let's see. Yeah, so that turned f of empty into empty of m. And now if I also rewrite with a g, then it becomes something that looks okay. Okay, and then it's going to be the same thing here, where we're asked to prove that this thing preserves multiplication, right? But this thing is f applied, g applied to f applied to whatever the argument is, and f preserves multiplication and g preserves multiplication. So if I have x and y.
Yeah, it's similar to all of the reasoning you had to do about map distributing over append and concat and so on, right? You have these auxiliary lemmas that allow you to push the function through, and so you just repeatedly push it through the various layers.
Right. So if I use the fact that f preserves multiplication, x, y, so I rewrite by that, then that has pushed, I mean, these goals are kind of horrible because things are infix.
Yeah.
But it's g applied to something, and the first thing, if you kind of unpack it, is f applied to x, and then it's f applied to y, and then we multiply these things together, right? So if we do another,
If you use it on the right.
if I use it on the right here, so I want to do the same thing for g, because now this is g applied to a multiplication is supposed to be a multiplication of g applied to things, right? So I think I can get away with just having Agda figure out what the arguments are if I use it on the right. Yeah. Okay. Then I also have to give an identity homomorphism. This is going to be a bit easier because I need a function from the carrier of S to the carrier of S. Well, I have the identity function. Now, I need to show that the identity function sends mempty to mempty. Well, it does because it sends anything to itself, right? So this is just riffle. And I have to show that the identity function sends x multiplied by y to x multiplied by y. But that's also just true, right? Okay. And then finally, so now I've given all the data, right? So I've said what are my objects? They are monoids. What are my morphisms? They are the functions that play nice with monoids. What's the identity and composition? Well, you compose the underlying function, so you take the underlying identity function, and this will play nice. But we also have to show that this composition is now associative and that the identity really is the identity, right? And if you try to just do this by hand, okay, let's maybe look at one of the identity ones first. So we are given a morphism from S to T, I'll call it F. And we have to show that, again, the infix things get in the way, but this is saying F, then the identity is supposed to be F, right? But how do we prove this? So we don't really have anything to pattern match on or anything like this, right? But what would we expect? We would expect two homomorphisms to be equal if the underlying functions are equal, right? All the data is really in the function. So homomorphism is a function that has some properties, that it preserves mempty and multiplication, right? So we could hope, I guess you didn't do this last week either,
No.
or prepared it. So we could hope if this is category of monoids, and could say when are monoid homomorphisms equal? It's kind of, because we need to answer this question in order to prove that the laws hold, right? So call this mon hom eq or something like this. So if I have f and g, which are homomorphisms from m to n, so I need to introduce m and n. Okay, and in the end I would like to say that f equals g, and my claim is that if the function of f equals the function of g, then this should be true, but I guess I need to say this, right? Okay, so let's see what happens. No, let's try to prove it first. So we have f and g, and we have a proof p that the underlying functions are equal. And our goal is to show that f equals g. So now, just to see what f and g are, right? I could pattern match on them. And it looks kind of horrible. So I'm going to call this one f, this one g, this is f preserves empty, this is g preserves empty, and this is f preserves multiplication, g preserves multiplication. Okay, so we have to show that these two records are the same. And we know if I pattern match on P by REFL, then this really is an F now, right? So we know that the first part of the records are the same, but these things could still be different, right? So the first thing I think I want to do is I just want to prove a little lemma which says that if I have two homomorphisms like this, I'll just call them f and g, and if all the fields are the same, so functions are the same, the empty-res proofs are the same, and the multiplication resp proofs are the same, then the morphisms are the same. So this is what I said up at the top, but I'm also throwing in that the other fields are the same, right? And the reason I do this is because this is easy to prove. Because if this is REFL, 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 okay, so I can't ask for these two things to be the same because they have different types. They only have the same type because of this first thing. So there's a standard trick to do? Have we done
Should
dependent
we-
pairs?
Should
Or I
we
could
just take
just,
the proofs offline? Should we push them later to the repository?
yeah, maybe this
Yeah.
is too much noise. I mean, normally we prepare this and give this to you. I guess what I could do this for a, no. Yeah, let's do this later. Let's just take this for granted for now, and we can still use it, right? I hope it's still something that intuitively makes sense. So we're saying that two morphisms are the same if the underlying functions are the same. And the way they manipulate the proofs doesn't really matter, because the proof, as Guillaume said, were boring, right? So then we could try to use that here, for example. Because here, well, sorry, we were in this one. So here, we want to show that F, which is a monoid homomorphism, is the same thing as composing F with the identity, which is also a monoid homomorphism, right? So this thing says that as long as we can do it for the underlying functions, then it's all going to be okay, right? But this is what you saw last week as well, right? That composing functions is often just works. So on the left-hand side here, we have the identity composed with F, which turns into this lambda x f of x, and on the right-hand side, we just have F. And we said that, well, the function that takes an x and applies F to it is the same as the function F, right? So this should just be ruffle. And the same way here, if I have F on the left, then what's left to prove is the same thing again. And here, for associativities, we are given F, G, and H. And we have to show that composing them in these two different ways is the same. But if we say, well, it's enough to show that the underlying functions are the same, then again, okay, it's again hard to see, but it's going to boil down to basically lambda x h of g of f of x, right? So therefore, it should just work here. Right? So the moral of that particular sub-story is give yourself the thing that does the sensible thing. And definitely don't try to prove this inline here, because that's really hard, right? But if you zoom out a bit, what we've done is we have made a category where the objects are really big in some sense. So if you have a monoid, then it's an object in this category. And the morphisms from one object to another are exactly the homomorphisms that play nicely with objects, right? So this is something you can often do. You have some kind of structure you're interested in, so you make these the objects of your category, and then you make the morphisms the functions between the structures that preserve the structure, right? And then you can do this whenever you have a notion of composition of these structured morphisms, and when you have the notion of an identity structured morphism that usually doesn't really do anything, right? Okay, what's next?
Yep. So there's another way to look at something a bit similar. So we said that categories were just fancy monoids. So let's do it like this. And you can actually make this more explicit by defining, or I guess should call it just fancying, fancier. You can take an arbitrary monoid and turn it into a category. So I'm going to give you a hint of how to do that, and then maybe you can just do it on your own time if you're interested. So what we said is that all the operations were the same, right? So I scroll back up. Where is it? All the operations were the same. Then an identity combining a neutral element. The only thing that we've done is that we've sprinkled some extra types to enforce that not all combinations are valid. They really need to agree in the middle. and then neutral is just at the same index. So what you can do is go in the other direction and just say, well, what if there's no interesting content in the indices? So in particular, if we import units, we know that unit has a single value inside. That's the trivial proof that this thing is true. And so all proofs of units are equal to each other. So if you pick your notion of objects to be units, then you can see that the type of then, oh, okay, no, I need to define morphisms too. And then your morphisms are not caring about the indices and just taking a value in the monoid carrier M. Then you can see that your definition of composition is now completely ignoring the objects because they're just boring. And you're just saying, well, if you have two values in this monoid carrier, you should be able to produce another one. And that's what combining gives you. And then for the identity, again, through computation, the indices disappear, and now you just need to produce a value in the monoid carrier. And then you need to prove the laws, associativity, identity, etc. That's exactly the ones you had for monoid. So you can uniformly transform whatever monoid you want into a category by just saying it has exactly one object, doesn't have any information in that object. And then the morphisms are just the monoids, the values in the underlying monoids. And so if you look at them in terms of morphisms, they're going from the one boring object back into itself. And then combining is just doing like multiple paths, always going back to the object. So here, there's no information, all of the information is stored in the morphisms, right? Because when you combine two of them, you still get something of the same type, but it has more information stored inside of it morally, because you've combined the two sub-things. Right. So then what I wanted to do was squish for categories. So just like we did squish for monoids, we can give ourselves an arbitrary category, which we can open. Categorte.
Maybe for now, Guillaume, you want to comment out the bits in the middle where the open goals?
Oh, yeah.
Including equality of monoid homomorphisms. Yeah. Just, okay. Well, it's used. If he has commented out, we're going to fix it later. Right, okay.
Okay. So if you remember, squish was going from list M. Okay, I should rename. Should I? So squish was going from list of M to M, where M was the underlying carrier for the monoids. But now that doesn't make sense anymore, because homomorphisms, M, which are equivalent to the objects, like in the monoids, are now indexed, right? They're the source and the target. So you can't just take a list of M's, like M need to be applied to something to become a set. So one thing you could do, I guess, is take S and T and say, okay, I'm going to take an arbitrary list of M of S and T, and then get to the target ST. But first of all, what do you do when the list is empty? How do you get from S to T? Maybe it's not possible to get from S to T. And then what do you do if you have more than one value in the list? You got from S to T, and then you have another way to get from S to T, but they don't compose. So you cannot actually squish them together to get something in the target. So that's where we realized that what we had list was giving us a bunch of values that were all at the same type. But if we want to squish a bunch of morphisms from a category, morally they need to be type aligned, right? If you take a first step, then the second one needs to take you from the target of that first step into something else. And then the third one from the target of that second step to something else. So we need to introduce a new data type that will allow us to do that. So I'll go back outside of the module and I can describe what it means to have a path according to, well, a notion of objects and a notion of morphism, which is indexed by these objects. And this will give us, I suppose I could fix the starts. Okay, so list was just telling us we had the type of values and then we could have 0 or more of them. Here it's a bit different. We have a type describing what it means to transition from a source to a target, and then we're going to describe what it means to have a path starting in S and going somewhere. So why did I make S uniform? Because I know that all of my constructors are going to start from S, but the target itself cannot be uniform because if you're not moving, the target is going to be the same as the source. But if you're taking a step, it's going to change, right? Because you're actually moving along. So that's how I picked between parameter and index. So just like for lists, we have the empty path where you're not doing anything, you're just staying in place. So it's going from the start to the start. And then we have the cons, which is taking a first step, and then you have a further path taking you somewhere else, and eventually you reach your target. So this is going to be
needed M after path.
Ooh, indeed, thank you. So if I can take a step, which is described by M, from the source to the middle, and I have a path from M, from the middle to the targets, then I have a path from the source to the targets. So now the M has disappeared from the index, but it's still type aligned internally. And now we will have the right notion, the right generalization of lists for categories, because we will have, again, 0 or more steps on the way. They will be type aligned, meaning that every single intermediate value sort of takes you along the path. And we will hopefully be able to produce a value that starts from the same start and ends up in the same target. So I just need to change that type a little bit. And right, I think this is just how we do it. And the code should be more or less, why is it doing this? Should be more or less exactly the same as the code that we had for the original Squish. Although I guess we ended up using Foldar, which we're not doing quite explicitly here. So if I have an empty path, it's taking me from the source to the target, which is exactly the same as the source. And luckily, I have an identity for this. Ooh. Why is it taking its argument? What? But I opened it. Oh, did we open it earlier? Okay. Yeah, whatever. Let's just use this one.
Yeah, this is one that's going to be annoying though, because it's infixed.
Yeah. favorite trick. We define a module that contains all of the values in the field, and now we can just mention them by name explicitly. And then if we look at this goal, well, we want a morphism taking us from S to T, and we have one taking us from S to M, and then once we're in M, we have an entire path taking us from M to T. Luckily, we already have defined squish, which can transform paths into proper morphisms. So we can just take the first step and then squish the rest of the path. Okay. And this is a big topic, so this I want to... Oh, I suppose one thing we could do. So last time we saw that squish was distributing over append, right? But we don't have a notion of append for paths yet. So we can define it. If I have a source, a middle, and a target, oh, this is going to be annoying. Okay. Just a bit of refactoring. These things are constant throughout. So,
You regret that.
yeah. Oh, this is so annoying. So this is the type-aligned version of append for lists, right?
Part of M and the types.
Multiple definition. So the previous append was taking two lists and combining them left to right. And here we're doing exactly the same thing. The only difference is that now we have the indices ensuring that the ends meet in the middle. And intuitively that makes sense, right? If you have two paths, you should be able to compose them. So it's defined the same way as append on lists by inspecting the first one. And if it's empty, it's not moving, so this is S to S, and the second one is S to T, and then we need to produce S to T. So we can just return the second one, just like we would for lists. And here, just like we would for lists, we take the first step, and then we append the two other paths. And so one thing you could prove now is squish plus plus. Too many equals. So if you want to have a go at this, it should be fairly easy. I think it should be exactly the same as the one on monoids. And tomorrow we'll look at proof by reflection. So a lot of the proofs that we've done today, well, could they actually be discharged? Maybe not. Anyways, the idea is that we can actually build some machinery to automatically prove equalities between values, between morphism expressions in a category. And we'll see how to do that.